we need to run this literally hundreds of times or thousands of times, and this model is way, way too small. So just consider the speed ups that we need on these different simulations is pretty incredible. This is some fluid dynamics stuff. This is done with Fluent, I believe. And here, this is a differential. It's looking at opinion gear and differential. Churning losses are significant. You consider that big, the large truck that I showed. Churning losses can eat up a tremendous amount of power, and we found that just through optimizing how the flow of the oil in some of these powertrains, we can reduce fuel or improve fuel efficiency by multiple percent. And on our large trucks, you consider the amount of fuel they're using. That's, again, very, very significant. Here's a full CFD model of a powertrain. This is just a differential, which would be similar to what you find in one of the large trucks. This model ran in 64 cores, I think, and took between 3 and 4 weeks on 64 cores. So very computationally intense. We can do some experiments, some research level designing, but if we get to the point where we're going to try to design all of our axles on all of our machines through simulation, this isn't going to work. We can't be running 3 to 4 weeks simulation. We need to get down to where this thing will run overnight, and we can run 10, 100, 500 of these different simulations in order to optimize it. Here's some of our combustion modeling. This is partly internal developed, partly developed at the university, and this is some of the technology that we use in order to develop the whole ACER engine for emissions. Some pretty amazing work, and again, very computationally intense. This is just a single cylinder. We need to go to multiple cylinders, and as we look at 6 or 8 cylinders, it's even more computationally intense. This is kind of the area that I live in, is looking at machine performance. And these are some examples of some full system models. This is looking at a loader dumping into the truck. And there are 2 things here. One of them is just kind of understanding the type of simulations that we do. Here we're looking at structural loading, so as these particles are impacting this truck body, we want to know what the stresses are throughout the truck body and then design it so that we can have the structural life. The other important thing is just looking at validation. So here we have some actual test data. We're putting that against our simulation and try to understand how to model so that we're able to have good correlation with what we see in the field. And in this case, we do. But having the model and not being correlated is of no value to us. So we always have to come back to correlating those models. Here's an example from our large wheel loader group, and this is the type of model that they run on a daily basis, trying to understand the performance, primarily structural loads. What we've got here is a discrete element model of the material, the implements interacting with that model. The forces are coming back through the system. You can see the stresses on this flex body model. We got the tire interacting with the earth. There's a full engine model in this. There's also a powertrain model. And then the other thing, which there should be a cab sitting right here, and in that cab, in the real machine, there's an operator that's operating this machine. In these models, in order to accurately predict our loads, we have to also be able to model or simulate the operator the way a real operator would operate a real machine. And so we also have operator models in there that are running this machine on the fly here during this simulation. So very complex simulation. This particular group, the large wheel loader groups, they have gotten to the point where they're doing most of their design just through simulation. So again, these are day-to-day models. They run these on a daily basis and make decisions.